Okay, hello everyone again. So in this video, we are actually going to jump a little bit and talk about the concept of independence. And so the concept of independence is really, really, really important in the field of statistics as a whole. One reason is because if it's a reasonable assumption for a particular problem, it can simplify that problem quite a bit. And so to introduce this idea, consider this example with a deck of cards. So the standard deck has 52 cards. There are 13 different values, ace, 2, 3, 4, all the way up to king. And then there are 4 different suits, spades, clubs, not puppy feet, clubs, diamonds, and hearts. And so we're given this problem. So given that a card is a face card, meaning that it's either a jack, queen, or king, what is the probability that that card is a spade? And so we'll define some notation first, because that's always useful to do. So we'll let F be the event that the card is a face card. We will let S be the event that the card is a spade. And what the problem is tasking us with doing is finding the probability of S given F. So remember, this is a conditional probability where we're trying to find the probability that the card is a spade, given we know already that the card is a face card. Okay. So we could tackle this problem just with the standard conditional probability definition. So probability of S given F is equal to their intersection divided by the probability that the face card, or that the card is a face card in the first place. So remember, essentially, it's we're considering the F as our new sample space, and that Venn diagram was the logic that we used. Okay, so we actually know both of these quantities already. So we know that the probability of a face card is 12 out of 52, because there's 52 cards, and there are 4 jacks, 4 queens, and 4 kings. We also know that the probability of the intersection is 3 out of 52, because there's only, out of the 52 cards again, there are only 3 cards that are both spades and face cards. So only the jack of spades, the queen of spades, and the king of spades. So what this means is that the probability that we're after is just 3 over 52 divided by 12 over 52, which simplifies nicely to 1/4. But we haven't really talked about independence. So, but probability of a card being a spade in the first place is 13 out of 52, which is also 1/4. And so really, in this problem, knowing F occurred tells us nothing about the probability of S. And so when this happens, when we know that F occurs, but it tells us nothing, it changes nothing at all about what the probability of S is going to be, then we say that F and S are independent. Ah, lovely. Okay. So that is kind of summed up in this first rule that I'm circling here. So two general events A and B are independent if and only if the probability of A given B is the same as the probability of A. So it doesn't matter whether we condition on B or not, we wind up with the same exact probability. That's what we just saw with this deck of cards example. An alternative definition, it just kind of also still uses that conditional probability definition, but events A and B are independent if and only if their intersection is equal to multiplying the probabilities of those two events individually together. And that's what we're seeing in this second definition of independent events. The two definitions are equivalent. And so what we're going to do now is we've got two more examples. In this first one, we're going to use the second definition just so we could see what that looks like. And then we will do a problem where we assume that events are independent, and we could see how we could use that assumption to simplify the problem. So first things first, this example says, suppose that you roll a fair six-sided die. It says event A is an odd number, and event B is an even number. And we're tasked with this question, are these events independent? Right away, you might be able to think logically that these events should not be independent. So knowing that A has happened, so knowing that the die roll is odd, that tells us something about the chances of B, because knowing it's odd means that B actually can't have occurred at all. But we will use the second little rule here just to verify that. So probability of A is, so 3 odd numbers out of 6, so that's 1/2. Probability of B is 3 even numbers out of the 6 possible rolls, so that's also 1/2. And the probability of the intersection is equal to the probability of the null set, because those two events cannot occur at the same time. And so that is 0. And so using that definition, we'll still do the calculation even though we don't really need to. We're just seeing that, 0 is not equal to a fourth. So A and B are not independent. Okay, getting fancy using this eraser. Wow, okay. So in other words, knowing that A happens tells us something about the chances of B and vice versa. Our last short example will let us use this independence assumption to simplify a problem. And so we are thinking about the 3 stoplights in downtown Canton, and we're assuming that the probability of getting a red light at each stoplight is 0.4, and that we have this extra assumption that the lights operate independently of one another. So the town didn't do it very smart, where you could kind of run through all the green lights and hit them all at the same time. We're assuming that it doesn't work like that, and that the lights operate completely independently. And so we're tasked with finding the probability that only the second stoplight is red. In other words, we're tasked with, so R1 complement, and R2, and R3 complement. So first and third are green, the second light is red. Because we have this independence assumption, that's what lets us do this next equality. Because we're making that assumption, that probability is equal to this. And so with that simplifying assumption, this is now a more straightforward calculation where since we know the probability of R1, we could figure out its complement. And same with the rest of the red lights. And if you calculate that out, you wind up with 0.144. So kind of two big goals. One is that we should be able to show whether or not two events are independent. And two, if we have independence, we can use that assumption to make a problem simpler. And this problem would have been impossible to do had we not made that assumption unless we had some more information. The last little bit here is just some extra facts about if A and B are independent, then A and B complement are independent, A complement and B are independent, and A complement and B complement are also independent events.